Hey everyone, so starting Unit 2, Lesson 4, hopefully you're doing okay with everything so far this unit. Make sure to jot down any questions that you have up to this point and check all of your homeworks and correct them as we go. We're going to talk about a couple of things in this lesson. The first one is average rate of change and net change, and this kind of actually just randomly fits with this one awkwardly. So just bear with me here. But average rate of change is essentially your slope at any given point in your function. So remember, we're doing some higher order functions here. So slope's not always constant, but you have your change in your y over the change in the x. You'll see that notated as this delta symbol, so a triangle. Or sometimes as like f of a minus f of b. So remember that's a way to write y, and then a minus b on the bottom. So the x's that match up with the y's. So again, essentially slope, but the 2 points that you use here are very specific, and we're looking at that average rate of change for a given time in your graph. The top of this function here, when we just look at the change in our y's, has a special name as well. And this here is your net change. All right, so again, looking at a function that is a quadratic, we know quadratics don't have a constant slope, but we can find the average rate of change and the net change between these two specific points. And so we do f of 1 minus, actually, let's flip this around. We'll do our larger one minus our smaller one. F of 3 minus f of 1. And this gives us our net change. So we'll just start with that. And we get that by plugging in these values for x. So we do 3 minus 3 squared minus 1 minus 3 squared. So 0 minus negative 2 squared. So 0 minus 4 is negative 4. So this is your net change. That needs to go on top of the change in your x's. So a minus b, or 3 minus 1. So over 2. And negative 4 over 2 is negative 2, and this is your average change. Okay, so between those 2 points, your average change is going down 2 over 1, essentially. All right, so here's another one for the function g of x equals 5 plus 1 half x. Find the net change and the average rate of change between these 2 points. G of x here is a linear function, so your average rate of change should be fairly constant, but we're still going to go ahead and solve this out. So we have 5 plus 1 half times 1. This is f of 1. So 5 plus 1 half. So I'm going to put 11 over 2. It'll be easier to calculate with it. F of 5 we need to find as well. So we do 5 plus 1 half times 5. 5 plus 5 halves. That's 15 over 2. And so again, we can find our net change by taking the difference between those. So 15 over 2 minus 11 over 2 gives us 4 over 2, which is 2. And this is our net change. Average change. We're going to then take that 2 and put it over the difference in our x's. So we have 5 minus 1. So 2 over 4, which reduces to 1 over 2. And I put the 5 first in case you're wondering why. I did f of 5 minus f of 1 because I wanted to keep this positive up here. And so I need to do the 5 first down here as well. Okay, so 1/2. And you can see if we look back at our equation that 1/2 was already there because this is linear, so that's a constant. Okay, so that's average rate of change and net change. Right. But now we're going to talk about transformations, and that's a little bit different. So you do transformations in geometry to a certain extent, where you do some rotations and translations and dilations and all of that. Now, we already talked about this in class today, so you should have your transformation handout. But just to go back over it real quick, so feel free to fast forward. Remember that x plus c is going to shift the graph, any function that you graph left, not two, sorry, c, number of units or spaces. And so like, for example, if you have x plus equals x plus 2 squared, this is going to go left 2, okay? A little bit against what we want to say since it's that plus sign, but that's the effect that it has because it flips it in there. And so your minus goes right. And that flipping it has to do with the values that make it 0. Remember, those are your solutions to your function. So this would be right 2. Actually, we can even use a different number so we don't get hung up on the fact that it has to be 2. And so those are grouped inside of your parentheses. They're always grouped with an x value in some way. So even in like a rational expression, so if we have something like this, I didn't mean to write a y, sorry. That 2 on the top is going to shift it left right because it's grouped with the x. So we look for things with the x, that's left right. Things grouped with the y or things in that constant position are going to move up, down. And so this shifts up C. So if f of x is equal to 3x squared plus 2, this goes up 2. Whereas a subtraction sign is going to shift it down. So if we have f of x equals the square root of x minus 5, this one goes down 5. If you have a number in front of your function, it's going to multiply it. And so you see that effect with the slope if we go with whole number values. So if you have something like y equals 3x squared, you're going to multiply the y values by 3, and so you're going to stretch that out. Whereas if you have like y equals 1/3 x squared, you're going to multiply the y values by 1/3, and so it goes, essentially it will go slower, and so it will shrink your function and keep it from going up as quickly. Negative signs are something else we talked about. Again, you have to pay careful attention to. So if a negative sign is on the outside, we're multiplying the y value by negative, and we're going to flip that over the x-axis, where if it is grouped with the x, so your negative sign is inside with the x value, we're changing our x values from positive to negative. So think about your table while we're doing, or think about your graph while we're doing this. If we flip the y values, all right, so we're multiplying everything so that the y is the opposite of what it should be. We're going from positive to negative or from negative to positive. So we're flipping over the x-axis. If we flip the x value where it's grouped inside here, we're going from this side of the graph to this side of the graph. So we're flipping over the y-axis. All right, so if you're graphing by parent function, so using all of the common functions that we did today in class, and just looking at, okay, this is the shift this way, this is what it does this way, then it's easier if you go in this order. So do any left, right first, then reflect over any axis, then shrink or stretch it, and then go up and down. It's just going to be, again, easier if you do that. Okay. So this one, be able to write out the transformations. So that will be a requirement that you'll need to do. So for example, this one goes right 2 and up 1. And so my parent function, I'm going to draw that here first, looks like this. Dot this line here. Okay, sorry. I wanted to, that's not really there. That's not the line we're graphing. So, but every single point in this graph needs to go right 2 and up 1. And so we're going to go right 2, up 1 with the vertex. And then this one goes right 2, up 1. This one will go right 2, up 1. Same thing, right 2, up 1, right 2, up 1. And so this is, let's call it function A. All right, we can see again the effects of that parent function here. This one, we have that negative sign out in front. So remember, it's not in parentheses. So it's reflecting over the x-axis. And then it's shifting down 3. And notice these are being written in the order recommended to do this by. And it's the same as your order of operations. This would happen before this does, if you were plugging in values for x. And you can always make an XY chart for any of these if the parent function is giving you trouble. Okay, so parent function is my dotted line here. I'm going to reflect over the x-axis. This one doesn't reflect, but then I'm going to shift it down 1, 2, 3. Okay, this one would reflect here, but then I shift it down 1, 2, 3. This one reflects to here, then I shift it down, right? And by this point, I should know that my parent function, this is where this next one is, just because I haven't stretched it or shrunk it, so it should have the same shape as that one there. But this is reflected 4 over, so I could go 4 and then go down 3 more, and there's my point. Okay. All right, this one goes left 3, stretched times 2, and then down 4. So remember, you're going to multiply y by 2. So whatever your y value is. So we're going to take again our vertex, which is at 0, 0, and we're going to go left 1, 2, 3. 0, our y value times 2 is still 0, and then we need to shift down 1, 2, 3, 4. Okay. Next point here, we have this point here. We're going to go 1, 2, 3. Our y value is 1 times 2 is 2, and then down 1, 2, 3, 4. All right, same thing here. We're going to go 1, 2, 3. We're here. 1 times 2 is 2, down 1, 2, 3, 4. I'm planting that right there. Here, we'll take this one here. We're going to go left 1, 2, 3. This y value is at 4. So if I double that, I'm going to go to 8. 1, 2, 3, 4 more. So this is at 8. So I would have a point here, but then that needs to move down 4. So I end up back here. All right. This one is going to mirror image that one because of the way quadratics work. And so I can just reflect it over this line. So I'll be here. And then I can draw my line. And notice how much more stretched out and how much skinnier that one is than my parent function. All right, so I know square root functions are fairly new, maybe. You should have done them a little bit in Algebra 2, but I want you to try this one. Here is your parent function. We have 0, 0, 1, 1, 4, 2, and then if you want to, you can go 9, 3. You don't really need that last point there, but it gives you one more to graph if you want it. And so this function looks like this. And go ahead and list the transformations and plot your points by transformation for that problem. If you would just pause your video, I will pop up the answers in a couple seconds. Okay, here's them all graphed out with their transformations listed out. Okay, so double check all your points, make sure they're plotted right, drawn right, make sure it matches what you described as your transformations. Okay, so now we can apply the same rules to writing equations. We didn't get to this in class. The graph of f of x equals x squared is a quadratic. We want to show that it's translated 19 units to the left. Remember, this is with your x. 14 units down, this is a constant, so plus or minus, in this case, minus 14, and then stretched vertically by a factor of 13. So this goes in front and then reflected in the x-axis, so we want that in front as well. And so we start by writing our equation, so x equals, okay, we want this grouped with our x inside the parentheses, so we have x left means we want this to say plus, it's always the opposite. X plus 19, quantity squared, it's still a quadratic. We need to go down 14, so we're going to subtract 14. We should be stretching this by 13, so vertically stretching by 13. and then reflecting. So that needs to be a negative 13. And then you have your equation, and you could type that in and graph it, double check with your parent function that it did what it needed to do. This part should look somewhat familiar from geometry. The graphs of f and g are given. Find the formula for function g. And so f you'll recognize hopefully as your common function or your parent function. So we look at those points there, and then we look at the points in g, we should hopefully be able to see what they're doing. So we're going to the right 2, then we are going up 1, and we are flipping it. So we are reflecting over the x-axis. And at this point, we can now write our equation. So we have f of x equals x squared as our original. We want to move that right 2, so we do x minus 2 squared. And we want to go up 1, so we're going to add 1 over here. And we want to reflect across the x, not the y. And so we're going to put a negative out front. And then the graph of the function is given. Use it to graph g of x minus 2. So we're shifting all of this down 2. This is outside of our parentheses, right? So we're just moving down 2. So every single point you just literally move down 2. And then you can redraw the line. And this next part is something we'll talk about. I'll let you know if it's on the test for sure or not. The original function, if your original function is even, then the opposite of your function is odd. And a mix of your function is neither. All right, tells you if you have symmetry. So we've talked about symmetry a little bit already with being a negative x. You sometimes get your original function, you sometimes get the opposite of your function, you sometimes get a mixture of the two. That tells you if it's even, odd, or neither. Even functions have y-axis symmetry. Odd functions have origin symmetry. So to determine if they are even, odd, or neither, you just plug in negative x. So we get f of x is equal to, we have negative x squared minus 2 cubed. So this comes out as x squared minus 2 cubed, which is our original function. And so this is even. Same thing here, we have f of x is equal to 3. We're going to plug in a negative x here. And we get negative 3x cubed minus 1. This is not the exact opposite because this constant sign didn't change. And so it is a mix. And so it is neither even nor odd. And the last one here, or if you would go ahead and do this last one here, these last two, and then we'll just stop the video there. So have a good night.